Welcome to the first video in our series focusing on chemical reactions. In this first video, we're going to introduce the basic theory about what a chemical reaction is, starting by what we mean when we say chemical change. So a chemical change occurs when one or more substances undergoes some sort of chemical reaction if it's involving more than one substance, usually when these substances are mixed together, and the reaction that results causes a new substance that did not used to be there to exist as a consequence of the reaction having took place. Now, as with most dictionary definitions, that's not really very helpful, so what we can do is specify that all chemical changes fall into one of three categories, starting with what we call inorganic chemical changes. Now, inorganic chemical changes are by far the most common example of chemical reactions that we're going to be looking at in this unit, and by definition, organic chemical changes involve the formation of a new substance from one or more original substances, and as long as these substances are not based on the element carbon, that means that they are classified as being inorganic. Now, why the significance of this name? Well, if we remember from when we learned about covalent bonds, there is an entire class of covalent bonds involving compounds where carbon is the central element, and these are, of course, what we call the organic compounds, which naturally introduces the next category of chemical changes that exist, which are what we call organic chemical changes, which, contrary to inorganic chemical changes, do involve carbon-containing compounds. And again, these don't need to be complicated. Every time you start a fire, for example, this campfire burning wood, the burning of wood, which releases two chemicals, carbon dioxide and water in its gas form, neither carbon dioxide nor water existed in this form in the wood, assuming that it was dry, but the burning of wood releases both of these chemicals that did not used to be there originally. So we can see, even though organic compounds can be quite complicated, many of the reactions are actually quite straightforward. Now, a subset of organic chemical reactions that we won't really study in this course because they usually fall under the domain of biology are what we call the biochemical chemical reactions, or just biochemical reactions. And these are any organic reactions because, again, they all involve carbon-based substances. Only biochemical reactions, and again, the prefix bio gives you a hint that these actually take place in living organisms and generally fall into one of two categories. The first of which are chemical reactions that are used by organisms to grow bigger, and the second category of reactions, what we call metabolism or metabolic reactions, are usually used in organisms for the purpose of producing energy. Now, to take a more detailed look at a specific chemical reaction, specifically an inorganic reaction, we're going to look at where water comes from. So here we can see that we don't actually start out with water, we start out with hydrogen gas, what we label as H2 for its chemical formula, and oxygen gas, what we label as O2 for its chemical formula. And these two, when we put them together in the right quantity, can react, which is why we call them the reactants. These are the substances that exist before the chemical reaction occurs. Then when we bring hydrogen and oxygen gas close enough together, we actually get our chemical reaction represented by this arrow here, and that chemical reaction produces a new substance that is neither hydrogen nor oxygen, but a combination of the two, which happens to be water. And the word that I use, produce, was deliberate because everything that occurs after the reaction has occurred are what we call the products. And rather than writing out the chemical structures, if we write out their chemical formulas sequentially like this, we can represent this chemical reaction as what we call a chemical equation. and interpreting and dealing with chemical equations is going to be the overwhelming focus of the chemical reactions topic that we're looking at in this series of videos. Now, one of the characteristics of chemical reactions is that they are generally considered to be irreversible. Remember that the word to reverse just means to go backwards. So what exactly do we mean when we say a chemical reaction is irreversible? Well, if we take water and flip it around so that water is no longer the product, water is the reactant, we can see that we actually have a different chemical reaction here. So by definition, remember, a chemical reaction is any reaction that produces a new substance or new substances. So here, if we treat water as the reactant instead of the product, we neither have oxygen by itself or hydrogen by itself. We have a combination of the two, and this chemical reaction here involves water breaking down and reforming as hydrogen and oxygen gas. So we can see that these two chemical reactions, the products and the reactants, are different from one another. In other words, chemical reactions are defined as being irreversible because they require a different reaction in order to be reversed. And that's why we call this reaction here the reverse reaction of the one that had occurred previously. And again, this is why we consider chemical reactions to be irreversible, because they require a different reaction, specifically the reverse reaction, in order to undo. Now, one way that we can simplify this whole concept of irreversibility is by looking at physical changes which are not chemical changes. So the best example of which is looking at water once again. Now, here we clearly have water in the solid form, also known as ice. Here we have water in the liquid form, and here we have water in the gas form. Now, everybody knows that all that we need to do is increase the temperature in order to melt ice, and then increase the temperature once more in order to evaporate water and turn it into gas. However, does this stop water from being water? Well, obviously the answer to that is no, because no matter whether water is in the ice form, the liquid form, or the water vapor form, we are still dealing with the same chemical, H2O. This is what we call a physical change rather than a chemical change. Specifically, we can refer to this as a state of matter change. So we can see that whether water is a solid, liquid, or gas is represented by a little subscript that I wrote here. S is for solid, L is for liquid, and G is for gas. But we can see that because the chemical structure of water, H2O, does not change regardless of whether it's solid, liquid, or gas, these are not actually chemical substances because no new substance is produced. The other thing is, if we want to get water vapor to turn back into liquid water, all that we need to do is drop the temperature again, and so we can see that state of matter changes are significantly easier to reverse than actually doing the chemical reaction that produces water. And most importantly, we can see that the actual chemical structure of water does not change during this entire process. For another example of a physical change that is not a chemical change, we can look at the dissolving of something that we are very familiar with in our food, sodium chloride. So here, when sodium chloride exists in its solid form, we have an Na plus and a Cl minus, a simple ionic compound here. Now, when we put this into water, does the salt disappear from the water? Well, it appears to, because it has dissolved, but does that mean that the salt is not there anymore? The obvious answer is no, it's still there, and we can find this out because if you were to drink this water, the water would taste salty. Now, this is a little bit different because the salt appears to disappear. That's a very strange sounding sentence, but what's happening at the chemical level is that the water that we've dissolved the salt in is pulling the Na and the Cl apart from one another, but it doesn't actually produce a new substance. We still have Na plus and Cl minus. We haven't made any new substance through the dissolving of salt. And if we want to show that this is easily reversible, if we were to boil the water, we would see the salt crystals left over at the bottom, meaning that because this is relatively easy to reverse, and because we haven't made a new substance, the dissolving of salt is yet another example of a physical change rather than a chemical change. So the conclusion here that we can reach is that physical changes may alter the shape of a substance. So obviously ice, liquid water, and water vapor are completely different in terms of shape. They may alter the size of whatever the substance is, or even as we see with the boiling and melting of water, we can alter the state of matter, but it doesn't actually change what the chemical structure of the substance is. And if this doesn't happen, we don't have a chemical change. The next video will expand on this because obviously it's difficult to see the chemical structure as a chemical reaction happens. So the next video will look at a number of different changes that we can actually observe to tell us whether a chemical reaction has actually occurred.